Hello everyone, welcome to you in Pune University. My name is Dr. Manish Singh and I am an associate professor in Mechanical Engineering Department. And this is video lecture series on basics of mechanical engineering. And this is lecture number 3 of Unit 1. And in this lecture, I am going to discuss with you pattern allowances. Okay. So these are the contents which I am going to cover in this lecture series: lecture level outcome, pattern allowances, shrinkage allowance, pattern allowance, draft allowance, machining allowance, shaking allowance, distortion allowance, and some multiple choice questions related to these topics. So at the end of this lecture, students are able to understand how to define pattern allowances, different pattern allowances, and what are the importance of all the allowances. They also understand what are the reason for considering these allowances, because these allowances are very essential for the casting process, and they apply this knowledge to design casting and identify the effect of inaccurate allowances causes in the casting process. So these are the some things, some knowledge that can be acquired by the students during this lecture. Okay, next let's start with this topic, that is pattern allowances. This is very essential for the metal casting process. And there are 5 types of allowances, that is shrinkage allowance or contraction allowance, draft allowance or taper allowance, machining allowance, or it also named as finishing allowance, taking allowance or wrapping allowance, distortion allowance or camber allowance. So generally these allowances are provided to the sand casting process. It is generally not used in the metal mold casting. And let's start with the first pattern allowances, that is a shaking allowance. So sorry, a shrinkage allowance. So first let's see why shrinkage allowance is required. This is the very essential question. So as far as the metal casting process, I already told in the previous sessions, the raw material is present in solid state. As you know that this is a raw material like a metal piece. This is present in solid state. And suppose its volume is V1, initial volume is V1. Now if we heat this pattern for melting, purpose, then this solid metal will be converted into liquid metal. And now if I see its volume, then obviously in the liquid state its volume will be slightly larger than the initial volume. Is it right? Let's say this is a V2 and this V2 is nothing but V1 plus delta V. Okay, why it happens, why its volume increases? Then you can see here, whenever a solid metal is heated and converted into liquid metal, then the breaking of atomic bonds takes place. Randomness always increases, and increasing atomic distance means, initially you can see if these are the two atoms which are exactly attached to each other, is it right? Initially in the solid state, when you start heating, then the interatomic distance will increases. And suppose initially the atoms are arranged like this, then their orientation will also changes like this, is it right? Randomness increases. So with the increase in heat or by conversion of solid metal into liquid metal, the bond starts breaking and the atomic distance will goes increases, and randomness of the atoms will also increases. And because of this region, the volume of the liquid metal increases, is it right? And now we need to pour this liquid metal into the mold cavity, is it right? So let's suppose if you want to produce a casting whose size is V1, is it right? Whose size is, let's say, V. So if you take a volume of V, and this is a solid state, this volume is for the solid state. So let's say this is a V1. Okay. So when you consider this volume for pouring of molten metal, then obviously this entire liquid metal increased volume is not completely we can say able to fill into this mold cavity, is it right? Some part of the molten metal is still remaining for the filling, is it right? And obviously after the solidification it will shrink, and because of this shrinkage the volume is slightly decreases. Is it right? So the size of the casting after solidification will be lower than the initial size. Is it right? To accommodate this shrinkage, this is called shrinkage. You can see here, during solidification this much amount of volume decreases. So this decreased volume is called as shrinkage. To accommodate this shrinkage, we always provide a shrinkage allowance. Is it right? So now the question is, so what is the suitable size of the pattern? Then obviously the suitable size of the pattern is exactly equal to the size of the liquid metal which I need to pour into the mold cavity. Is it right? Not V1, it is equal to V2. And obviously V2 is since slightly larger than V1, therefore pattern size will also be slightly larger than the pattern exact side of the casting. Is it right? So this increased volume we need to accommodate, and this accommodation process is called as shrinkage allowance. Is it right? So now you are aware with why shrinkage allowances is required, why volume increases. Is it right? Now if I draw its cooling curve, let's suppose if you fill the molten metal at this temperature, which is higher than the its solidification temperature. Why we increase this more temperature? This is called as degree of superheat. This is called as degree of superheat. Okay. Why this degree of superheat required? You can see here, when you pour the molten metal, you just see once again, which I already explained you, but once again you can see, when you pour the molten metal, then molten metal needs to follow a certain distance, yes or no? And when it flow from this pouring basin to this certain distance, then it required time for filling, and obviously during this flow some heat may goes out. Is it right? And if you use this exact liquidification temperature, and when you start pouring and slightly if it's heat removed, then the solidification begins, and even the chances arises before filling this mold cavity the metal gets solidified. Is it right? To accommodate this time period up to which the liquid metal is required for complete filling of the mold cavity, we always provide some degree of superheat. Is it right? So this is called degree of superheat, and this temperature is called as pouring temperature. This temperature is called as pouring temperature. Pouring temperature means it is a temperature at which the molten metal just fill the mold cavity. Is it right? And now you can see, since this is a cooling curve, so when we move from pouring temperature to freezing temperature, then you can see here the temperature decreases, yes or no? And because of this decreased temperature, the randomness of the molecules also decreases, and hence the overall volume of the molten metal will reduces. So this reduced volume is called as liquid contraction. Now the question is, why it is called liquid contraction? It is called as liquid contraction because this entire contraction takes place in the liquid state. That's why this is called as a liquid contraction. Is it right? And next, once the temperature reaches to freezing temperature, this is the beginning of freezing temperature. Means once the temperature reaches to this temperature, then solidification starts. So this TF is called as freezing temperature. Freezing temperature. Is it right? So this is the temperature at which the freezing just begins or solidification just begins. And in this sense, the phase, this you can see here phase change takes place. Is it right? Phase change takes place. Is it right? Phase change means liquid metal will be converted into solid phase. Okay. So during the phase change, as we know that the latent heat will remove from the system. Therefore, the temperature is remain constant, and this entire process is called as solidification, and the contraction associated with this phase change is called as solidification contraction. Is it right? The contraction of the or reduction of the volume associated with solidification is called as solidification contraction or phase change. Is it right? Next, once the metal reaches to this point, the entire metal gets solidified, but still its temperature is much bigger, much higher. And even if I talk about with reference to steel, then this is around 1400 degrees centigrade or more than 1400 degrees centigrade. Is it right? So obviously the solid material at this high temperature, it is not useful for any application, and even that this temperature automatically decreases when it exposed to the atmosphere. Is it right? So further analysis is also required. Obviously at this point the metal gets completely solidified, but still till room temperature we need to analyze it, and this temperature represents room temperature. Is it right? This represents room temperature. So obviously when temperature of the casting decreases from uh, free, uh, this freezing temperature to room temperature, then because of this reduction in temperature, the contraction of the metal, overall metal, takes place. Is it right? And this contraction is also called as solid contraction. Is it right? Solid contraction. Why it is called solid? Because in this the contraction of the metal takes place during the solid state only. That's why this is called as solid contraction. So you can see here in this analysis, when we pour the molten metal and the solidified it up to the room temperature, then three-stage contraction of the three-stage of the molten metal takes place. Not molten metal, metal takes place. First stage, that is liquid contraction. Second stage, that is solidification contraction, and third stage, that is solid contraction. Is it right? These are the three contraction takes place during the casting process, and we need to accommodate these contraction. Then obviously you can see here, initially in first and second stage of contraction, since the liquid metal is still available. Is it right? In this liquid metal is still available, it means if you provide some extra liquid metal to accommodate this contraction, then it can be easily accommodated. Is it right? And for this we just simply use a riser. Is it right? So for first two stage contraction we always use riser. Is it right? This is a riser, and its purpose is it acts as a molten metal reservoir, and it provides liquid metal during solidification in the mold cavity. Is it right? So this is a molten metal reservoir, and it contains liquid metal, and during solidification it provides liquid metal to accommodate the liquid and solidification contraction. Is it right? And obviously after the completion of solidification, it is not possible to add extra liquid metal to accommodate that contraction. Why? If you provide liquid metal, then it is separate, it is solidified separately, and both liquid metal and solid metal which already solidified does not mix properly, and if does not mix properly, then they make layered structure. Is that right? And if it makes layered structure, then by applying some load it can easily separate it. Is that right? Therefore riser design is not suitable to accommodate solid contraction. So now the question is, since riser is not suitable for solid contraction for accommodation of this, so what is the way through which we can accommodate this? Then obviously this solid contraction is accommodated by pattern design, and I am interested in this only during this stage. Okay, pattern design. Correct. Now the question is how pattern design accommodate the solid contraction. So let's say in the next slide. Then first I'm going to summarize the cooling curve. You can see during solidification its volume decreases. To compensate this decrease in volume, shrinkage or contraction allowances are provided. The total contraction of the casting takes place in three stages. You remember this, three stages. The contraction of the liquid from the pouring temperature to the freezing temperature, contraction associated with the change of phase from liquid to solid, and the contraction of the solid casting from freezing temperature to room temperature. And obviously I already told you first two stage contraction is compensated by riser design, and the third contraction is compensated by pattern design. Is it right? So we need to analyze both the things, but in basic mechanical engineering syllabus we only have pattern allowances. Therefore I am not discussing about riser design. Is it right? Next let's see how pattern design accommodates the solid contraction which takes place during the casting process. Okay, so let's suppose this is a casting whose size is, let's say this is a 100 millimeter, this is also 100 millimeter, and this is 100 millimeter, and the whole its size is 20. Is it right? All dimensions are in millimeter, so I'm not writing everywhere. Is that right? So this is our actually product which I need to produce, and for this we need to make a casting. Is it right? Then obviously, as you know that the delta L thermal strain is nothing but this is a coefficient of thermal expansion into delta T. Is it right? Where alpha is the coefficient of thermal expansion and delta T is a temperature. Is it right? And this is called as thermal strain. Thermal strain. Is it right? And alpha is a coefficient of thermal expansion. And this is material property, and this is temperature change. Okay, this is temperature change. Okay, so thermal strain can also be written as delta L by L naught, and this is thermal, which is equal to alpha delta T. So from this delta L thermal can be written as L naught alpha delta T. Then obviously for a given casting material, for given casting material, alpha and delta T is remain constant. Okay, remain constant. The only variable is temperature, sorry, length. Is it right? Different the length, different will be the contraction. Is it right? So that's why it is represented by, this is represented by this contraction is represented by contraction per unit length. Is it right? Because I already told you delta L thermal is nothing but this is L naught alpha delta T, and since alpha and delta T is constant, so delta L thermal completely depends upon the L naught. That's why it is represented by amount of contraction per unit length. So for example, if I write for some materials and their contraction delta L by L naught per unit length, if I represent, then you can see for cast iron it will around 10 millimeter, okay, per meter, 10 millimeter per meter. Similarly for steel you can see here this is around 20 millimeter per meter, and for aluminium it is around 18 millimeter per meter. For copper alloys it is around 16 to 17 millimeter per meter, and for the zinc it will be around 24 millimeter per meter. So these are the some example of contraction allowance. Means if you make a casting of cast iron whose length is 1 meter, then during a solidification solid contraction 10 millimeter shrinkage takes place. Is that right? 10 millimeter shrinkage takes place. Correct? So now if I need to calculate, if this is a cast iron, this is a casting made up of cast iron, then what is the size of the pattern? Then the size of the pattern is always generally we make slightly larger than the actual size. So simply if I add the amount of contraction takes place with the original dimension, then we can accommodate the shrinkage contraction. Okay, sorry, solid contraction. So this is 100, this is actual size plus how much contraction takes place. So you can see here in 1 meter 10 millimeter contraction takes place. Is it right? Means in 1000 millimeter around 10 millimeter contraction takes place. So what in 1 millimeter length how much contraction takes place? Obviously this is 10 by 1000. Okay, it means if you want to calculate contraction for x millimeter length, then simply can I say here you just multiply this factor 100 by 1000 into x, then actually you will get the how much actual contraction takes place in x length. So by using this concept, simply here I am writing 100 is the x and the contraction allowance is 10 by 1000 for cast iron. Is it right? So after simplifying this, you will get 101 millimeter. And what about this? This is, since this is also 100, so I'm not writing for this again. This is 101. This is 101. So if you make a pattern with this size, then you will get the correct accurate casting. Is it right? And now if I talk about internal features, these are the external features. Now for the internal features, if I want to make a hole, then obviously we need to provide a core. This is a core. This is not a pattern. Is it right? So in the core, in case of core, remember the size of the core must be slightly greater than the exact size of the core. Is it right? Let's suppose instead of 20 millimeter, you need to make a 21 millimeter. Why? Because this casting is filled with a molten metal like this. Is it right? And solidification is always takes place opposite to the direction of heat transfer. So you can see in this the heat transfer takes place along this direction, heat transfer takes place along this direction, heat transfer takes place along this direction, and heat transfer takes place in along this direction. Therefore, the net the contraction of the metal takes place towards the center. Therefore, this molten metal try to shrink this core. Therefore, if we make slightly larger core, then obviously by this metallostatic pressure applied by the liquid metal during solidification, it compressed and then we get the exact shape of the hole. Is it right? So this is all about with the help of this example, we understand how we accommodate the shrinkage allowances. Is it right? Next, a draft allowance or taper allowance. Then you can see here, if you see this figure, correct? And this is a molding sand, and this is a pattern. And now when you fill this molding sand with the around the pattern, and after ramming, when we start withdrawal, then you can see due to the continuous contact between pattern and the molding sand, you can see like this. If this is a sand wall and this is a pattern, that they have a rubbing action between them, and because of this rubbing action, what will happen? The molding sand may dislodge and maybe collapse. Is it right? To prevent this collapse, we need to create a contact break between the pattern and the molding sand. Then how we will create? Then obviously it is happened due to the flat surface. Is it right? But instead of flat surface, if you make slightly taper this pattern, then obviously you can see this gap, the size of the pattern and the gap, we have slight difference. Even the gap is more than the pattern size. Therefore, the complete contact between the pattern and the sand wall is prevented or break. Therefore, during withdrawal, both surfaces cannot erode to each other. Therefore, without sand erosion or collapse, we can easily produce the casting. So this tapering of the tapering of the pattern is called as draft allowance. Is it right? So now the question is, whose dimensions or what surfaces require tapering surface? Then obviously those surfaces which are parallel to the direction of withdrawal is require a tapered surface. You can see we only provide this vertical taper surface, not this horizontal taper surface, no horizontal surfaces. Is it right? So taper always provided to those surfaces which are parallel to the direction of withdrawal. Is it right? Like this. So I think from this discussion you can understand how why we use a draft allowance or taper allowance, and obviously it is used to prevent the sand erosion while the withdrawal of the pattern. Is it right? Now the question is, after suppose if you make a tapered pattern, is it right? Actually you need to make a pattern like this, but instead of this you need to make a forcefully you need to make a tapered pattern. Then obviously if you make a taper pattern, then you will get a taper casting, and after solidification you just remove this extra material by metal cutting, then you will get the defect free casting. Is it right? Then you will get the desired shape and size of the casting. Is that right? Next, machining allowance or finishing allowance. Okay, then obviously I already told you in the metal casting process, the surface obtained will be having very poor surface finish. Is it right? And if it is poor surface finish, then obviously for getting a accurate surface finish, we need to provide some machining. Yes or no? And during machining, obviously some of the material may removed. Yes or no? And if some of the material get removed, then to accommodate this reduced size, we need to make a slightly bigger casting than the actual size. Is it right? And for making bigger casting, we need to make a bigger size pattern. So this increased size of the pattern is called as machining allowance. Is it right? So machining allowance will be take care of the extra material that will be removed, obtained a finished product. Is it right? Like this, if I need to make a casting of 100 millimeter size, so if I need to remove 1 millimeter from each side, then obviously for this you need to make a 102 size pattern instead of 100 millimeter pattern. Is it right? So the total size of the pattern is 102. Similarly, this is 102 and this is 102 if it is made by 100 by 100 by 100 casting. Is it right? Next, secking allowance. Now, if I talk about the secking allowance, then obviously if you have a pattern like this, if I draw it's a top view, then it is looking like this. Okay, this is a mold box, and here we have molding sand everywhere. Okay, and this red portion represents the pattern. Okay, this is the pattern actually, and now we need to withdraw this pattern. So actually foundry person what they did actually, by putting a pin, they just start shaking along this direction and shaking along this direction in the horizontal plane. Is it right? And when we they shake, then the bond between the pattern and the molding sand will break. And if it breaks, and why it breaks? Because uh, due to this shaking, the size of the mold cavity slightly increases. Okay, and because of this, the bond will break, and then now the pattern can easily be withdrawn. Okay, so obviously due to this shaking action, the size of the mold cavity slightly increases. To accommodate this increased size, what I need to do, we need to make slightly smaller than the pattern size should be smaller than the actual casting. Is it right? So that's why this is called as negative allowance. Is it right? And there is no mathematical expression through which you can determine this. So this is experimental based and this is skill based. It depends upon the skill of the operator. Is it right? So this is called as taking allowance. Next, distortion allowance or camber allowance. You can see here distortion or camber allowance. See, sometimes see if you need to produce a thin casting. Okay, let's suppose this is a thin casting. And now when you pour this thin mold cavity with molten metal, then because of this metallostatic pressure applied by the metal during solidification, the entire casting may be distorted. Is it right? Let's say distortion takes place in this direction. And now the question is how you are obtained in which direction the distortion takes place. Is it right? Then obviously it is only depends upon the experiment. When you perform experiment, then you will get the direction of distortion. And suppose if your casting get distorted during solidification like this, then to accommodate this distortion, simply you just provide opposite distortion of the pattern itself. Okay, and if you distorted this pattern, then during solidification it will may staten. Okay, so this forcefully distortion provided in the pattern is called as camber allowance. Is it right? Or this is also called as distortion allowance or camber allowance. Is that right? So vertical edges will be curved or distorted. This is prevented by shaped pattern converging slightly so that the casting after distortion will have its sides vertical, and the distortion in casting may occurs due to the internal stresses. Is that right? Why it has happened? When you pour the molten metal and when you allow solidification, then during solidification all the molecules are coming closer to each other. Yes or no? Then because of that its volume decreases and hence some internal stresses may also arises. Is it right? And because of that internal stresses, the casting may be distorted. Is it right? So the countering of this distortion is very essential because this distorted product cannot be used for any application. Is it right? So to accommodate this distortion, we provide a camber. Is it right? Why it is called camber? Because we just provide this distortion in the opposite sense of the pattern. Is it right? Therefore, when you solidify this metal inside this cambered part, then automatically it gets statened, and hence you will get the accurate casting rather than the cambered casting. Is it right? So this is all about all types of pattern. Is it right? So in this in this lecture especially, we saw what is how many types of allowances are there and how to provide these allowances for the pattern design. Is it right? So we start with the shrinkage allowance, and especially shrinkage allowance is very essential, and major allowances shrinkage allowances play a major role in the design of the pattern. Is it right? And then and of course for the easy withdrawal, for the defect free casting, we also need to make a taper allowance, then machining allowance for getting proper surface finish, then shaking allowance for the easy withdrawal, and the distortion allowance for the distortion of the material. Is it right? And now let's see some MCQ questions. Okay, which of the following allowances compensates for metal contraction during cooling? Then obviously during cooling, shrinkage allowances takes place. Is it right? Which of the following allowances compensate for metal contraction during cooling? So the right answer is shrinkage allowance. Okay. Draft allowance is provided too. So allowances for material shrinkage prevent distortion in the casting. No, wrong answer. Facilitating easy removal of the pattern from the mold. So the right answer is option C. Is it right? Draft allowance is provided to facilitate easy withdrawal of the pattern from the mold cavity. Okay. Next, machining allowance increase the strength of machining allowance is given to increase the strength of the mold. No, this is wrong. Ensure clean surface after machining. Yes, this is right. Easy the removal of pattern. No. Prevent shrinkage. No. So the right answer is option B. Machining allowance is provided for getting the accurate or better surface finish. Is it right? Next, which material requires the largest shrinkage allowance? Then obviously in cast iron, brass, aluminium and steel. Steel is having maximum shrinkage allowance. I already told you in steel we have around 20 millimeter per meter. In aluminium we have around 17 or 18 millimeter per meter. In brass we have around 17. This is approximate data, not exact, but somewhat it is looking like this. So the right answer for this is steel. Okay. And at the last, which of one of the following is negative allowance? Then I already told you, shaking allowance is a negative. This is the only allowance in which we need to reduce the size of the pattern, and rest of the allowances we always need to provide slightly bigger pattern over the actual casting. Is it right? So this is all about pattern allowances and some MCQs related to this topic. So thank you for watching and good day to all of you guys. Let's meet in the next lecture.